Grabbing that doorknob after a mid-afternoon nap could be a real shocker. Stay tuned to find out why. Hi, I'm Robin DeMarco, the online physics teacher, and my passion is to demystify physics and then supercharge your physics learning experience. This has happened to most of us. We've laid down for a mid-afternoon nap, then somebody comes to the door, rings the doorbell, you get up, you shuffle across, you grab the doorknob, and zap! All of a sudden you're wide awake. What happened? Why did you get a shock? You didn't have a charge on you, did you? It's wintertime here in the United States, and that means that our furnaces are running quite frequently. We have dry air now, which makes this perfect time for static buildup. And that's what we're dealing with today, is a static charge. To understand statics, let's take a trip over to the whiteboard. Matter is made up of three separate parts. We have something called protons, and these are positive charges that are in the nucleus. We have electrons, and these are negative charges that orbit. Then they're going to be in either energy levels or layers, depending on who you talk to. Energy shells is another term that you may hear. And finally, we have something called a neutron. And a neutron is nothing more than a neutral charge or neutral mass. And it's also in the nucleus. So let's draw a picture of what this actually looks like. We'll start off by drawing three circles here. These are going to be our protons. And then we're going to have three more. These would be the neutrons. And finally, we're going to actually put on the electrons. The electrons, remember, go on the outside. They're going to be orbiting here. So we'll have one over here, and maybe we've got one over here. And we'll put the third one over here. Okay, and what they're doing is these are actually, remember, they're orbiting. So they're going to be kind of coming up and around something like this. And this is a static or a neutral atom. If we look at all the parts, all right, we see we have three positives. We have three negatives. Oops. And we have three neutrals. And when we add that all up, it equals 0. This atom has no charge on it. But what happens when we move one of the electrons? So here's our nucleus, and now let's put our electrons, but this time, instead of having 3, we're only going to put in 2. All right. Now, what does that do for us? Well, it'll help to think about what's actually going on with this particular atom. In this case, we have 3 positive charges. We then have 2 negative charges, and we have 3 that are neutral. Now, this gives us a positive charge, a positive 1 charge. So in this case here, by losing an electron, we lose an electron, we become a positively charged ion. Where did the electron go? Well, what's actually happened is it got stripped away by something. So let's take a look at another atom that may have been the part that was close by. And in this case, instead of having only 2 or 3 electrons, it's got an extra one now. Let's see. So if we do the addition over here, what we're going to see is that we now have 3 positive charges. I now have 4 negative charges. And again, we have our neutral charges. And this is going to equal a -1. So if we gain an electron, we end up with a negative ion. Now, this is really what's happening when we grab that doorknob. As we shuffle across the carpet, we're losing electrons. We're becoming charged. When we grab that handle, we're discharging. Nature wants everything to be equal. So what's happening is the electrons will try to balance out. Now, it may not come out perfectly back to 0, but what will happen is you'll actually have an equal number on both parts. You may both have a little charge, but it's going to be an equal charge. Now, one thing we see as we go through these is that if we have a positive charge and a negative charge, these attract. You've heard the old saying that opposites attract? Well, here they are. A positive charge and a negative charge will attract to each other. However, if I have a positive and a positive, or a negative and a negative, these are going to repel. They're like charges. They don't want to be next to each other. They want to be with the opposite charge. So they're going to push away from each other. Now, a quick way to figure out if things are attracting or repelling is take a look at the math that's here. If I take and put a multiplication sign between each of these, a positive times a negative gives me a negative. But a positive times a positive gives me a positive. And a negative times a negative gives me a positive. So what we see is that if the sign of the charges, if the sign comes out when you multiply them together, comes out as a negative, the force is attractive. If they're pushing apart, they're going to have a positive sign. Charles Coulomb came up with a way that showed the relationship between these attractive and repulsive forces, the charges that are involved, as well as the distance between them. And it looks a lot like our equation for gravity does. In this case, it's the force, and I'm going to put Fe for electrostatic force, is equal to 1 over 4 pi epsilon naught Q1 Q2 over R squared. Now, this is called Coulomb's law. Now, depending on what book you're using and what level class you're taking, will depend on how they actually write Coulomb's law, because you'll notice that 1's a constant, 4 is a constant, pi is a constant, and so is epsilon. So really, this 1 over 4 pi epsilon naught is a constant, which we can call k, and that constant is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. And what I've found in the past is that textbooks that are geared toward engineers, calculus-based texts for physics will tend to use the 1 over 4 pi epsilon naught. The algebra-based ones tend to use k. Same thing, works out the same. So what we can actually do is we can show that this is also equal to k Q1 Q2 over R squared. And this is called Coulomb's law. Okay, let's go take a look at an example. So we're asked to find the force of attraction between an electron and a proton that are separated by a distance of 1.5 times 10 to the minus 4 meters. Okay, so what we're going to do here is use Coulomb's law. And as always, we're going to start off by writing out Coulomb's law. I am going to use the algebraic version, so K Q1 Q2 over R squared. And for K, remember it's 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. And now we're going to look up the values, the charges for an electron and a proton. And we find that a proton is 1.6 times 10 to the minus 19 coulombs. And an electron is negative 1.6 times 10 to the minus 19 coulombs. And the distance in this case is 1.5 times 10 to the minus 4 meters. Don't forget that it has to be squared. Okay, going through and doing the math on the top, we get it's minus 2.3 times 10 to the minus 28 Newton meters squared. And the bottom gives us 2.25 times 10 to the minus 8 meters squared. Do some division here, we get a negative 1.02 times 10 to the minus 20th newtons. We use 2 sig figs everywhere else, so we're going to use it here. And we'll see that as minus 1.0 times 10 to the minus 20th newtons. And that'll be our final answer. Since the sign is negative, that tells us that this is an attractive force. So if I was to draw this out, what I would see is that I would have the proton here, electron here, and the forces would be going toward the middle. Well, I hope you saw that Coulomb's law is pretty easy to handle, pretty fun. So if you found this video helpful, please give me a thumbs up, like the video, hit the subscribe button, and if you haven't already, be sure to follow the link down in the description and get your free copy of 15 tips on how you can improve your science grade today. Have a great day.